this complex matrices, section 4.4. Okay, we have studied the symmetric matrix for a real matrix. Then we studied the Hermitian matrices that has these properties. And this matrix, the matrix that whose transpose is same as A, and it is symmetric, the complex matrix. This matrix is called a complex symmetric matrix. Complex symmetric matrix. This Hermitian matrix is a natural generalization of the real symmetric matrices. But complex symmetric matrix is not a direct generalization of the real symmetric matrix. This is a different class of the set of matrices. Okay, when we need to know about the properties of this complex symmetric matrix, this is needed in the study of regular analytic mappings of the unit disk in the complex plane. In this part of the mass area, we see Grunsky inequalities that talks about this inequality, where Aij is a log of this and Bij is a log of that. Here, this matrix is Hermitian, and this matrix B is complex symmetric. Okay, this is also can be used in the area. Here's the example that when this Grunsky inequality is used, when f of x is a regular analytic function on the unit disk, and f of g is normalized so that f of 0 is equal to 0 and f prime of 0 equal to 1, then f is 1 to 1. F is 1 to 1 if and only if the Grunsky inequality holds for all gi's in C with its radius is less than 1. So this inequality gives the condition the f of g to be 1-to-1 function. And also, when A0, A1, A2 are sequence of complex numbers, then we can form a 2n by 2n matrix, a 2n whose entries are ai plus j from this sequence. Then this matrix is called the Henkel matrix. This Henkel matrix is an example of complex symmetric matrix. Okay? And there are some theorems by Nehari that shows one if and only if statement on the existence of Lebesgue measurable and almost everywhere bounded function. And also it has some analog of Schur's theorem that A is in Mn, then there exists a unitary matrix U and upper triangular matrix delta such that A is equal to U delta U transpose if and only if A conjugate has all eigenvalues that are real and non-negative. And this is example. When we have A such as this, that is a real symmetric, that is a complex symmetric matrix, then this A can be written as this. eigenvalues are real and non-negatives. And also, one other interesting theorem on complex symmetric matrix is Takagi's factorization. Is there anyone who knows about Takagi, Japanese mathematician? Takagi. Haven't heard about? He is the father of Japanese modern mathematics. He is the one who had his bachelor's degree in 1897, bachelor's degree from Tokyo University, and he went to the Göttingen University in Germany for a couple of years, and he learned from German mathematicians. And he came back to Japan, and he wrote his PhD thesis in Japan, and he earned his PhD in 1903. And this is about time then we also studied the modern mathematics in Korea. In Japan, they started it and they continued to produce a PhD. He's the second PhD in whole Japan. He's the second PhD. But he is the father of all 20th century Japanese mathematicians. All field medalists and all have their root on this Teiji Takagi. He started real Japanese mathematics in 20th century. Okay, so every mathematician knows him. Every Japanese mathematician knows about Teiji Takagi these days. In Korea, we are trying to find a role model like Teiji Takagi. And now, Im-hak Lee is the one who did pretty much of the similar role that Teiji Takagi did, because he taught many math major students who became PhDs. And Im-hak Lee is the first PhD, the first Korean PhD in modern sense. And he guided many Korean mathematicians who became PhD and good professors and researchers. And also he helped many of his juniors to study abroad in the second half of the 20th century. Okay. So you should know Teiji Takagi and Im-hak. Then they had a pretty much similar role for the development of early stage of Korean and Japanese mathematics. And Takagi showed this theorem. When A is a symmetric matrix, there exists a unitary matrix U and real non-negative diagonal such that the matrix such that A is equal to U sigma U transpose, like you saw before. Here, the columns of U are eigenvalues of A conjugate, and the columns of U is the ON set of eigenvectors of A conjugate. Okay. And corresponding diagonal entries sigma i's are square root non-negative square root of eigenvalues of A bar. This is what Takagi showed. In here, columns of U are also ON set, also normal set of eigenvectors of A bar, and sigma i's are the non-negative square root of eigenvalues of A conjugate. So it's supposed it has a mu1 and mu2 and set mun, then the sigma I is the square root of mu I. Actually, square root of mu I. Actually, this gives us all very interesting matrix factorizations later. Proof is quite rather simple. If A is complex symmetry, then A bar is a complex conjugate of A. Then A conjugate is same as A conjugate transpose. Okay, this is a Hermitian matrix. This is a Hermitian matrix. So if X is not a zero vector, then the eigenvector of this Hermitian matrix and A star x is equal to lambda x, then x star lambda x can be written in this way and can be written in this way, can be written in this way. Then lambda can be written in this way, and we know that this is non-negative. Then the symmetric matrix A is positive semi-definite because all eigenvalues are non-negative. Okay. And so it's positive semi-definite. Then by theorem 4.43, there exists a unitary matrix U and upper triangular matrix delta, such that A is equal to U delta U transpose, where delta is has main diagonal entries all sigma i's, and all sigma i's are non-negative. But U delta U transpose is A, so A transpose can be written as U delta transpose U transpose. But that means, because U is a unitary matrix, so U can be U is equal to delta is equal to delta transpose. What that means is delta is a diagonal matrix. And also, all the diagonal entries are non-negative, so it's delta is a non-negative diagonal matrix. Okay. Finally, A conjugate can be written in this way, which can be written in this way. But here, this is a Hermitian matrix, so it's this is unitarily diagonalizable. It's also already unitarily diagonalized. So the columns of U are the eigenvectors of A conjugate. You have shown all this in chapter unitarily similar, chapter 2. Yeah. So this is not a difficult proof. This is quite clear. Just after you know the Schur theorem, then this is consequence of Schur theorem. And Takagi studied it on the complex symmetric matrix and found this. And this also leads up to the polar decomposition and singularity decompositions. Singularity decomposition is this. A is a complex matrix. Then there exists a unitary matrix V and W. And diagonal matrix sigma such that A is equal to V sigma W star. This is called the singularity composition. And the diagonal entries of this sigma is called the singular values of A. This is SVD. That starts from here. Okay. This Takagi's factorization is when A is a complex symmetric matrix. It is a special case of singularity composition. Very short. When A is equal to this, then Takagi factorization can be made in this way. You can think A and A conjugate. You can find the eigenvalues of it. You can find the square root of it. Okay, non-negative. And what? And also you can find eigenvectors. And eigenvectors and normalized eigenvectors give you this one, and these eigenvalues give you this sigma. So you have delta, and delta from here, u from here. That gives you the Takagi factorization. Yeah, there are some others. The symmetric normal matrix is some characterization of it. It has some better factorization. Here, but the difficulty in the examples, and we must have this where this. Yeah, the others are not that. I haven't seen much, but as you see, this Takagi factorization lead us to the singularity composition, which will be very important, not only 50 years ago, but also these days and for the days that will come. Okay. Any questions on section 4.4?